In the early 1970s, the search for extraterrestrial intelligence stopped being a fringe idea and started looking like a real research program. Radio astronomers focused on a simple logic. If another civilization wanted to be noticed, it might send a tight, artificial-looking tone. Nature usually spread radio energy across many frequencies. A narrow signal, concentrated into a small slice of the dial, felt like the kind of clue science could actually test. That logic pushed attention toward one special landmark in the spectrum, the hydrogen line near 1420 megahertz. Hydrogen filled the universe, and this frequency sat in a quiet part of the radio band, making it an obvious place to listen. At Ohio State University, a large radio telescope called Big Ear took on that job. It did not chase targets. It surveyed again and again, letting the sky drift through its view and logging what the receiver heard. Big Ear's surveys were built around discipline, not drama. The system watched for narrowband hits near the hydrogen line and recorded them automatically, line after line, as numbers on computer printouts. Most of the time, those numbers described ordinary background and familiar radio noise, but the method mattered. It meant nothing depended on someone's mood or a lucky glance at a screen. If something unusual crossed the beam, the telescope would treat it the same way. On August 15, 1977, Big Ear kept doing what it always did, letting the sky drift overhead while its receivers listened. Then, in the steady stream of numbers coming out of the computer, one patch of data rose fast. It was stronger than the usual background. It sat in a tight slice of radio frequency, not spread out like most natural noise. And it arrived at the exact pace the telescope's sweep would allow. Because Big Ear did not track targets, it could not hold on to anything it found. The sky moved through the telescope's fixed beam, and any source got only a brief moment to show itself. That timing mattered. The signal climbed, peaked, and then fell away, matching a drift-through detection rather than a random spike. The whole event lasted about 72 seconds, long enough to be real, short enough to vanish. The printout captured it as a narrow-band burst, concentrated, clean, and unusually intense. That combination carried weight because a thin, focused signal looked more like a deliberate transmission than a messy, natural process. But the same mechanics that made the timing fit also closed the window immediately. As the beam swept past, Big Ear moved on. Whatever produced that radio energy stayed behind in the data and nowhere else. Days after the night the printout rolled off Big Ear's computer, the paper reached a new set of eyes. Astronomer Jerry Eman went through it the way scientists often did then, line by line, looking for anything that stood out from the usual stream of numbers and symbols. Most marks meant nothing. Most spikes meant noise. Then one short sequence broke the pattern. It read 6EQUJ5. To a casual reader, it looked like random characters. To the people who worked with that system, it acted like a quick intensity code, a shorthand that climbed from weak to very strong. This string meant the signal had surged far above the background and then faded, all within the brief window the telescope had on that patch of sky. Eamon did not file it away as just another oddity. He circled the code right there on the printout and wrote a single word in the margin. Wow! That small reaction changed everything that followed. A technical anomaly gained a name, a handle scientists could point to, debate, and chase. From that moment, it stopped being a line of data and became an event. Investigators treated the printout like a crime scene and rebuilt the signal from the few numbers it left behind. First came frequency. It sat near 1420 megahertz, right beside the hydrogen line, a natural radio marker that astronomers watched closely. That placement mattered because it looked intentional, like it had been chosen to stand out. But it also raised a hard question. Was it truly on that exact forbidden line, or just close enough to imitate it? Next came bandwidth, how wide the signal spread across the dial. This one stayed narrow, more like a single tone than a noisy broadcast. That narrowness matched what engineers expected from a purposeful beacon, because narrow signals cut through space more cleanly and were easier to spot. Yet the data also showed limits. The telescope system measured in coarse steps, so the signal's true width and drift could only be bounded, not pinned down. Precision remained just out of reach. Then they worked the sky position. Big Ear did not steer. The sky slid through its beam, so timing became location. From the 72-second rise and fall, they narrowed the source to a patch near the constellation Sagittarius, with 2 possible spots because of the telescope's dual beams. That fit the Milky Way's crowded center, where many natural radio sources lived. A beacon could have come from there. So could confusion. The reconstruction made the signal look plausible and still unprovable. After the signal's basic details got pinned down, the next step sounded simple. Look again, in the same place, at the same frequency, and see if it came back. Observers scheduled follow-up runs and aimed their attention at the coordinates tied to that brief 72-second sweep. They listened around 1420 megahertz, where the strange spike had appeared so cleanly. This time, the printouts stayed ordinary. Nothing rose above the noise. That silence mattered more than it seemed. A repeating signal could have been checked, measured, and tracked as the sky moved, turning one surprising detection into something solid. Instead, every new pass produced the same result. No narrow-band carrier at that spot, no matching strength, no second chance. The team widened their searches slightly, in time and frequency, to catch any drift or small error. Still, the source refused to show itself again. With each failed attempt, the meaning of the original burst shifted. It stopped behaving like a steady transmitter and started looking like a rare event, something that happened once and then ended, or something that crossed the telescope's view only for a moment. That created the central problem. Science needed repetition to confirm a discovery, but the only thing available was a single line of data. The signal stayed famous. The sky stayed quiet. The months turned into years, and Big Ear kept doing what it had always done, sweeping the sky again and again, waiting for another clean spike at the same spot. But the second signal never arrived. Every new pass that came up empty changed the meaning of the first detection. What had sounded like a door cracking open began to look like a single knock that never came back. That absence mattered because science relied on repetition. One strong printout could be a real transmission, but it also could be a rare glitch, a brief burst of interference, or something nobody had anticipated. Without a repeat, there was nothing to measure twice, nothing to test under the same conditions. The wow signal started shifting categories, from possible contact to unexplained event. Skeptics leaned hard on that point. A single, non-repeating detection left no way to confirm a source, no way to track a pattern, and no way to rule out ordinary causes with confidence. The famous characters on the page stayed compelling, but the evidence stayed thin. Over time, the burden quietly flipped. It no longer needed an extraordinary explanation. It needed any repeat at all. With no repeat to chase, attention drifted from distant civilizations to something closer and more awkward. People. Radio telescopes did not just hear space, they heard Earth too. A stray transmission could slip into the receiver, get boosted by the system, and look more important than it really was. So the question shifted. If the signal had been human-made, what could have produced something that sharp and brief? Satellites became a prime suspect because they crossed the sky and carried radios of their own. In theory, one could have passed through the telescope's sensitivity pattern and left a 72-second trace. But the details caused arguments. Many satellites did not transmit at that exact frequency, and their signals often smeared or drifted, not staying neatly in one thin slice. Still, the sky held enough hardware that investigators could not dismiss it. The clean, narrowband profile kept pulling the debate in two directions. Some scientists treated it as a fingerprint of intention because nature usually spread energy out across many frequencies. Others pushed back. Narrowband did not automatically mean alien. It could also mean a very ordinary transmitter seen in an unusual way. Reflections, side lobes, and brief alignments could fake cleanliness. The signal stayed impressive, but its purity stopped being proof. By the 1990s, the Big Ear telescope no longer felt like a permanent part of the search. The program ran into a simple, unforgiving reality. The facility sat on land that could be used for other purposes. Funding and priorities shifted, and then the decision landed. Big Ear shut down. For a mystery built on one brief recording, that closure carried a heavy consequence. After the shutdown came the dismantling. The very system that had produced the WOW printout, its hardware, its signal chain, its way of sweeping the sky, went away piece by piece. That mattered because science relied on repetition. When something appeared once, the next step usually meant recreating the same setup and trying again. With Big Ear gone, that exact test stopped being possible. The search continued, but it had to move on to other instruments, other surveys, and other ways of listening. Those telescopes could look toward the same part of the sky and tune to the same frequency, but they never matched the original conditions perfectly. The WOW signal stayed locked to a specific moment in a specific machine. One detection remained one detection, and the door to a direct replay closed for good. In the 2010s, the WOW signal gained a second life. Better digital archives, newer software, and more complete records let researchers recheck old assumptions with fresh eyes. One idea rose above the rest: a comet. The claim sounded simple. If a comet passed through the right patch of sky, its cloud of hydrogen could have given off radio energy near the same frequency the telescope logged. The comet hypothesis shifted the mystery from aliens to chemistry and timing. Comets carried large halos of hydrogen gas, and hydrogen naturally emitted at a well-known radio line. Supporters argued that a hydrogen cloud drifting through the telescope's beam could have created a strong spike and then vanished as the sky moved on. It offered a one-time event without requiring a transmitter or a repeat performance. But the same details that made the comet idea attractive also gave critics ammunition. They questioned whether a comet's hydrogen could have produced a signal that narrow, that strong, and that clean. They challenged the timing too, asking whether any comet actually lined up with the recorded position during those exact minutes. The debate revived the case, but it also underlined a hard fact. Even the best news story still had to match the old numbers. Decades later, the technology changed, but the verdict did not. New radio telescopes covered wider areas of sky, checked more frequencies at once, and listened with far better sensitivity than Big Ear ever had. Computers also searched in real time, flagging anything that looked unusual. If a signal like "wow" had been common, these systems should have caught others. They did not. The famous burst stayed alone, with no twin to back it up. At the same time, radio astronomy entered a new phase, hunting short-lived events. Fast radio bursts, pulsar glitches, and other brief flashes proved the sky produced plenty of one-off surprises. That made a single strong blip feel less like a message and more like a category problem. Without repetition, a signal could not be tested, tracked, or pinned to a source. It could not be separated cleanly from rare natural events or stray interference. So the wow signal stayed in an uncomfortable middle ground. It never turned into a confirmed detection, but it also never collapsed into a simple explanation everyone accepted. In practice, it became a reminder of how science treated extraordinary claims. One data point did not carry the weight. The mood shifted from the 1970s hope that one perfect printout might change everything to a quieter conclusion. The burst remained an unresolved anomaly.